Okay, some examples here of finding the curve of, now it's not the least squares fit, it's what you might call log linear. These are some non-linear relationships, something like these. Trying to find the a and the b. Well, here the a and the b, the a and the, well, this one actually doesn't really make sense, but anyway, and the a and the x here, or possibly the a and the s, whatever. So this is what you undertake. First, you write it in the linear form. You make new x and y values. Then you do the normal linear least squares method to widen mx plus c, which means these equations here, these normal equations, the multiplier of c is 1. So multiply everything by 1 and add up. And then the multiplier of m, which is, I appreciate, a little bit confusing, is x. Multiply everything by x and add up. xy, add up, mx squared, add up, cx, and add up. Find the m and the c and then convert back to the original constants. Because the m and c here will be in terms of, say, a and b, you're going to have to convert back. Okay, let's see how these questions look. Right, so let's delve into the story. We may as well, because the stories also kind of explain why we learn these things. They kind of give examples of where you could possibly use these in a project or possibly in work. Consider a light beam of span L with load per unit length of W of x. The deflection of the beam at any point is given as the solution of the fourth order differential equation. We're going to learn about this in chapter 2. And from this, a formula for the maximum deflection can be found. So the Wi are somehow loads. L is the length of the beam, Young's modulus, and that's the second moment of area. Okay, so these are kind of formulas for maximum deflection of, for example, a simply supported beam, something like this. It's not always possible to solve this thing for any possible load, or it mightn't be possible to solve exactly where the deflection is, although that's a slightly different thing. In this case, if you can't solve the exact equations exactly, you've got a number of options. You can do some approximation stuff like chapter 4, or you actually could come up with what's called an empirical law. Now, in general, a lot of the equations or formulas that you use that have decimals in them, they're empirical laws. So rather than someone solving some equations and finding out what the real story is, people just did a load of measurements and fitted the curve to the measurements, and they said, oh, this is the law. This is the kind of thing. This is called an empirical law. Empirical just means law, a formula based on data. So in one of these cases, when you can't solve it, coming up with an empirical law is an option for a maximum deflection formula. Suppose an engineer measured and recorded the maximum deflections delta of cantilevered beams of the same Young's modulus and second moment of area and a load W that depends on x and L only for different values of L. Now, x is just the distance along the beam. So basically what this means is as long as you know the length of the beam, you can find the maximum deflection. And it's saying that the load only depends on them. So like it could be something like, oh, I don't know, it's a certain type of load that's proportional in a weird way with the span. Okay, so this is some measurements. They did a 4 meter beam, found this maximum deflection, 5 this, 6 this, 7 this. So it's hard to come up with what the formula is. That's something probably not for today. It's more level 8 and even possibly level 9 or something else. But anyway, we'll give you a formula. After plotting the data, the engineer believes that the data has a relationship of this form. Now this, by the way, will give you an idea. This is well, actually this is polynomial. So it could be like L squared, L cubed, L to the power of 2.5. As I said, if you see decimals, typically you're thinking it's an empirical law. Just give or take, it looks something like this. Okay, but it's not in linear form. Okay, so the first thing is write this in linear form. So you have a multiplication instead of addition. If you look at the previous lecture, if you have a multiplication and you want an addition, the thing that turns multiplication into addition is log. So I'm going to take the log of both sides. So log of delta equal to log of a times L to the n. And I'm going to yeah, we probably have space here. So the multiplication, logs turn multiplication into addition. So this is log of a plus log of L to the power of n. And we also know that logs turn powers into multiplication. So instead of to the power of n, it's going to be multiplied by n. So I get log of a plus n times log of L. Now, this has to be in the form y equal to mx plus c. The y is easy. It's always going to be log of the left-hand side. So this is going to be the y. Now we need a constant times a variable. Now it's easier to come up with the variable. Here you can see, because there's data for it, L is a variable, L is changing. So if L is changing, log of L is changing. So this is the variable. This is like the x. And therefore the n must be a constant. Okay, so it must be mx. Oh, sorry, this should be log of L plus log of A. So this is y equals m. The x is log of L plus the c is this. Okay, that's part one done, and we're on our way. So the hope would be if you actually plotted log of delta versus log of L, you get a straight line, and that's something we can deal with. So it says hence find the best values of n. Now it's just looking for n because essentially, I suppose n is the power. So this is actually this is called the power law. I might just write that down. And like the power kind of tells you what's going on. So yeah, that's right, power law. So for example, the maximum bending moment on a simply supported beam, it's the power of L is 2, so it's a power law. Okay, so the normal equations are done with y equal to mx plus c. So the multiplier of c is just 1. So multiply everything by 1 and add up. So y by 1 is just y and add up. Mx by 1 is mx and add up. Take out the common factor m. Plus add up the c by 1 is c. Add up the c's. And then we also have that the multiplier of m. So the point is we're gonna kind of forget about delta and L and work with m and x. The multiplier of m is x. You can kind of work with log of delta, log of L, but to my mind you get a bit confused. So the multiplier of m is x. Multiply just in this black thing here. Multiply everything by x and add up. xy add up. Mx by x is mx squared and add up, take out the common factor m. And then c by x is cx, add up, take out the common factor c. Okay, so what we need to do, and hopefully there's good space for it on the next page, is, and I might need a different pen if I have it, is we need to make we need to add up the y's. We need to add up the x's, add up the c's a little bit different, add up the x by y, add up the x squared. Okay, so what we have to do after this though is we need to tabulate what is x. X is log of L, and it's the ln one, not the log, and y is the log of delta. So I think we're going to do this on the next page. Yes. So log of x. Now they're kind of done for us here. Excuse me, x is log of big L. So the big L, the first value is 4, so I do ln of 4 is 1.386. Does it say anything about significant figures? It says 4. Okay, so we can do it the whole time. This will be the log of L equal to 5, log of L equal to 6, log of L equal to 7. Now we need to take the log of the deltas. So we have log of, the first delta is 5.12. For significant figures, 1.633. The next one is log of 12.5, 2.526. The next one is log of 25.92, 3.255. And the next one is log of 48.02. So you can see the the deflection is growing very, very quickly. 5, 12.5, 25.92, 48. So that indicates it's like the power is going to be quite big. 3.872. And we need to add these up because we need to know the sum of the y's. So 1.633, you can see here why you want to restrict to so many significant figures. It's a bit messy otherwise, although a bit easier with Excel. 2.526 plus 3.255 plus 3.872. I'm very bad, I'm always pressing the wrong button on the calculator. 11.29. Okay, and then x squared. Oh yeah, and it was important maybe to write down that this was the log of the delta. Now you kind of forget about delta and L. Okay, so x squared, we're not squaring L, we're squaring x. We're squaring the log of L, so 1.386 squared. There's no shortcut here, by the way. You can't square that. Like we'll see that in a minute. So 1.921. It is way easier in Excel, which is actually where you'll be doing it. 2.589. 0.792 squared. 3.211. And 1.946. 3.787. Now I want to add those up. 1.921 plus 2.589 plus 3.211 plus 3.787 comes out to be 11.51. Okay, and then x by y, this by this, and again, like, look at this number here. It's nothing like this squared. Similar story. This number is nothing. It's not going to be like 11 by 6. It's not going to be anything like 66. So we need to do this by this. 1.386. You can see how this is quite tedious in an exam situation. You won't have that. 2.263. I have 1.609 by. Now, did I do the right thing there? I'm not sure I did. I think I did the x by the x squared, which is wrong. It should be x by y. 1.386 by 1.633. No, I did all right. So it's probably difficult here to see if you did go wrong. Yeah, let me just keep on going. 1.609 by 2.526, 4.064. 1.792 by 3.255, 5.833. I appreciate this isn't a very interesting lecture video, but this is how this is what we got. 3.872. So that gives 7.535. And we add these up. So 2.263 plus 4.064 plus 5.833 plus 7.535. And it comes out to be 19.70, which, as I said, is not the same as add up x by add up y. They're not the same. So this gives us normal equations, which are from here. Now I'm going to do it with add up the x times m plus add up the c equal to this, because I want to get multiple of m plus a multiple of c equal to a constant, etc. So m times add up the x is m, this times m. So 6.733 m plus add up the c's. So there's just 4 points here. So it's c, 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 4c equal to add up the y's, which is 11.29. And then the other normal equation is m times add up the x squared, which is 11.51 times m plus c times add up the x, c times the 6.733c equal to add up x by y, 19.7. Now here is, if you were to solve this for m and c, you certainly want to solve for both of them. And because it's all decimals, you probably want to do Cramer's rule. Here actually, it's only interested in the power, It's not interested in the a so much. It's just interested in the general behavior. So it just wants the n. Now we have to go back and find out what is n. N is the same as m. So we want to solve this for m. And one of the things, and as we said, m is equal to n. One of the other things about Cramer's rule is if you want to just find one of them, it's handy. You don't have to solve both. So, and it's decimals anyway. So I think normally in class I wouldn't solve this, but here we'll do a little Cramer's rule. So m, which remember is the same as n, will be what I call dm over d. The d bit is easier. I bet it won't come out as this as well because there'll be different rounding errors depending on how you solve it. So we'll see what we get. So the d is the determinant of the coefficient matrix here, 6.733 for 11.51, 6.733, and then dm is the same thing, but you replace the coefficients of m, these two, with the constants. 11.29, 19.70, and you still have the 4 and the 6.733. Now space isn't great, so I'm probably just going to do this all in one go to 4 significant figures. So I'm going to do right down diagonal minus left down diagonal on top, 11.29 by 6.733 minus 19.7 by 4 on top. I particularly don't need to store them if I'm not finding the c. 6.733 squared because it's multiplied by itself minus left hand diagonal 4 by 11.51, and I get out 3.939, but it rounds up, so I get 3.940. Oh, thankfully it's the same. So yeah, so one of the things actually here is if you wanted to find a, what you won't actually end up with, you won't find a, you'll find c, which is log of a. So from this you can solve for c. And so say if you did that, you say c is equal to whatever, but this is actually log of a. So you get log of a is equal to whatever. And then how do you get a? Well, what's the inverse of log? It's exponential. So in this case you would do the exponential of both sides, and you would get a is equal to the exponential of whatever this is. So that's what it means by convert back to the constants. Here we'll see just what did we actually do here. Just by fitting a curve to the data, we can find an empirical rule for the deflection. So it's a formula that comes from data. In this case, it's roughly that the deflection is 1/50th of L to the 4. And you see the thing is here, you can see the general behavior. If you double the span, L0 to L1, which is twice L0, look what happens. The deflection is multiplied by a factor of 16, which is 2 to the power of 4. So that's why this question is only really interested in the power. That kind of gives you the general behavior, the general gist of what's going on. Okay, so I think in the next question, hopefully we'll find, we'll have to do that log messing around.